In this video, I want to look at the basics of graphing logarithmic functions. And we should look at the graphs of logarithmic functions in the same way that we look at any other function, as a set of inputs, which we usually call x, and a set of outputs, which we can call y, or f of x. And our graph is a visual representation of all the possible inputs and outputs, and it allows us to look at them so that we can see the behavior of the function at different points. First, we can consider the parent function for logarithmic functions. So we could say that p of x is equal to log base b of x. This is our most basic version of the logarithmic function. And what you'll note here is that we have log base b. Much like our parent exponential, p of x would have been b to the x, our base can be any number b, and that's useful, but we also might want to use a specific number to be able to graph and visualize. So in this case, we're going to treat our function that we look at as f of x equals log base 2 of x. Now you could use any base, but I find 2 to be nice and easy to work with to visualize the effects here. But just know that it could be any base b. And when we want to graph something, typically we want to plot a table of values and sort of explore the behavior and sort of make some conclusions about the graph. So I'm going to set up a table of values comparing x and f of x, or y. And I'm going to start by plugging in a 1 for my x value. So this means that I would be taking f of 1 and looking for my output. So log base 2 of 1, I'm trying to see what does that equal. And this is a way of saying 2 to what power is equal to 1? The answer is 0. 2 to the 0 is equal to 1. So we are going to say f of 1 is 0. An input of x gives us an output of 0. And we plot that right on our graph. And this is our first key feature of our graph. These graphs don't have a vertex per se, but this is the point that could be considered your most key inflection point of a logarithmic graph. Okay. Now I'm going to plot 2 as my input. So I'm going to take f of 2 is equal to log base 2 of 2. And this is saying 2 to what power is equal to 2. Well, 2 to the first is 2. So I put in 1 as the output, and I plot my point, 2, 1. And I'm going to do one more point like this. So I'm going to say 3, and we can put f of 3 is equal to log base 2 of 3. And this is asking 2 to what power is equal to 3? And the answer is, well, that's a little bit more complicated because we need some sort of decimal value. And a calculator could probably tell you that. But for just exploring this graph, it doesn't necessarily make sense to use 3. So we're actually going to go back and we're going to change our input to something that's a little easier to conceptualize. So we're going to change our input to 4. So we're going to say f of 4 equals log base 2 of 4. 2 to what power is equal to 4? Well, 2 to the second power equals 4. Okay. So notice how I'm picking my inputs so that I get really easy points to plot on my graph. If I'm making a graph by hand and I don't really want to have to guess with decimals, I want nice integer values, I need to do a little thinking about what does a logarithmic function mean? What points should I plug in so that I get nice integer outputs? Okay, and this is going to continue. Now, next interesting point would be 8, because 8 would be 2 to the third power. So I'm going to put in 8, 3, and then we would have 16, 4, which is somewhere off this graph. And we see that we're starting to have this behavior of growth. We can plug in increasing values of x, and our outputs will increase forever. We can always increase our outputs as long as we are able to continue increasing our inputs. But what about in the other direction? What happens if we, actually let's keep that for a second, plug in 0 for x? So if I want to take f of 0, that means I'm taking log base 2 of 0. And this is saying 2 to what power is equal to 0? Well, there's nothing. This is undefined, because if we just repeatedly multiply by 2 or divide by 2, there's no way we can end up at 0. So we call this undefined. There is no such value. Okay? And maybe we want to see what happens if we have a negative number. So let's try -1, like f of -1 is equal to log base 2 of -1. And that's saying 2 to what power equals -1. But we run into the same problem. 2 is a positive number. I cannot raise it to some power, right? I cannot multiply it by itself or divide it by itself and end up with a negative value. So this is also undefined. And what we end up with is an asymptote at x equals 0. We will never be able to input 0 or any negative number and get an output. So one feature of our logarithmic graphs is that we have an asymptote at x equals 0. We have a vertical asymptote on our parent graph at x equals 0. What about between 0 and 1? This is the last area to consider. So we've looked at positive integers 1 or greater. We said those all work and we can keep increasing forever. We looked at negative numbers. Those don't work. We can't get negative outputs. Or sorry, excuse me, we cannot have negative inputs. We can get negative outputs, but we cannot have negative inputs. And we looked at the input of 0 and we said that doesn't work. But let's look in between there. So what if we were to put in, for example, 1/2? Okay, let me move this real quick. If I put f of 1/2, this is saying log base 2 of 1/2, or 2 to the what equals 1/2. And knowing our rules of exponents, 2 to the -1 equals 1 over 2 to the first equals 1/2. So our output here is -1. So this is why we can have negative outputs, despite not being able to have negative inputs. I plot my point, and I can keep going. I can put in 1 over 4. So f of 1/4 is equal to log base 2 of 1/4. And this is saying 2 to what power is equal to 1 over 4. Well, 2 to the -2 is 1 over 2 squared is 1 over 4. So our log base 2 of 1/4 is -2. So we continue to decrease, and we can input increasingly small fractions and continue to output increasingly negative numbers. Okay. For example, let's just do like 1 over here. If I erase this all. If I put in f of 1 over 512, that's equal to log base 2 of 1 over 512. Well, 2 to what power equals 1 over 512? Well, 2 to what power? 512 is equal to 2 to the -9th. 1 over 512 is. So we say 2 to the -9th would be, or our output is -9. So we can continue getting more and more negative numbers as long as we keep increasing this denominator or making smaller and smaller fractions, closer to 0. Okay, so our end behavior of this function, as x increases, y is going to go towards infinity. As x tends towards 0, y goes to -infinity. So let's wrap this up. We're going to talk domain, range, and end behaviors. Oops. Let's delete this. Okay, so we said that our domain of our function is from 0, not inclusive, to positive infinity, which we could write as x is greater than 0. Our range of this function is all real numbers, or -infinity to positive infinity. And we also can mention the end behavior. So as x gets increasingly large, we can put infinitely large values of x into this function. Our f of x, our output, also goes towards infinity. As x tends towards 0, from the right side, right, as we go towards 0, we are able to get increasing negative values. So as x goes to 0, as we get closer and closer to 0, our outputs get more and more negative, all the way towards negative infinity, and the opposite in the other direction. And you'll notice that this is the exact opposite of exponential functions. Exponentials have infinite inputs, you can put all real numbers in, but their outputs are only y is greater than 0. And as inverse functions, they have opposite domains and ranges. Okay, so those are some of the key features of logarithmic functions. That's how we would go about graphing them. They have vertical asymptotes, and in the parent function, that vertical asymptote is at x equals 0.